then you can actually fabricate the tube from a drug, or you can coat this tube using a drug, or you can use it to manipulate things. It's moving, it's having hard time, then it will move toward this cell, and it will stay for future time in this orientation as you see over there. And what we're trying to do now, we are controlling we are fabricating these microbeads, and we are trying to achieve better coupling between the sperm cells and the microbiotic systems. Yes. So eventually, I would like to thank members of my group, the medical robotics group at the German University in Cairo. These are the students and faculty members who are actually contributed in these experiments. And thank you very much. And I will take the questions.
Doctor, if I loaded the drug on the micro-robot or the magnetic bacteria or something, and the drug is delivered, how do I get rid of this micro-robot? Isn't it toxic or something?
Yes, some of them are toxic. Let me repeat the question, okay? So we have an excellent question here. And the question is, if I took some of these micro-robots inside my body, how am I going to get rid of them? It's a very nice question. So the first thing, all these microbeads must be biodegradable. So we should let's say fabricate these microbeads from biodegradable materials. The second thing, if you are using bacteria or sperm to move, let's say, drug capsules, there's no harm. There's no harm. True. For the magnetic bacteria we are using, it's been proven that it does no harm for our systems. I don't hear you fine, I'm sorry. Yes. Why don't you take a mic?
Doctor, you said that the sperms were covered with copant, right? And naked, if I remember, right?
True. Yes, true.
Yeah, this is very toxic inside our bodies, so we use sperms.
Yes. Well, yeah. One of our applications is biomedical, but we still want to use this microbot in other applications. Yes. So, when you have this, let's say, a group of microbots, just don't use the one that will cause harm. How about this? There is a robot that's injecting oxygen. You don't want to have oxygen in your bloodstream, right? So don't use it for biomedical application, but you're right, you're 100% right.
Okay, thank you.
Thank you.
دكتور هو احنا ازاي بنتارجت السيل اللي احنا عايزين نوصل لها دراج مثلا؟
Yes. Okay, thank you. I will repeat the question again. How can we target? Well, what we do is we fabricate our microbes using magnetic material, right? Then we have to know the disease cell. If let's say the cell is spread all over the place, it's a very big problem. But let's assume that we have some tissue and the disease is localized. If the disease is localized, we will just orient the magnetic fields in a way that will take the robot towards the change reference position, but in this case, it will be the disease cell only, by controlling the magnetic fields. Well, does that answer your question?
Dr. Sima, if you allow me, I have two questions.
Please.
The first one is, can these robots have intracellular functions like enzymes? Can they enter the cell?
Well, thank you. Just let me also repeat the question. It's a very smart question saying, well, can this robot drill the wall of the cell and stay over there? That's nice. because he's thinking, why don't we fabricate this microbe from a drug? It will live inside the cell, it will kill the cell, let's say, or it will, let's say, heal the cell. It's been done. It's been done by Professor Thomas Maluk in Pennsylvania State University this year. He has nanorods, just like the ones that we have. He's fabricating them in his lab, and he managed to move his microbe, let's say, toward the cell, and he penetrated the wall and stayed over there. A lot of microbes, he managed to do this. It's been done in Switzerland by Professor Pat Nelson, ETH theory. Okay, he had spiral microbes, 5 microns in length. He managed also to kill the cell. Yes.
My second question, I'm a medical student. Can I pursue further studies in this?
Of course you can.
In Egypt.
We are doing these experiments in Egypt.
The Jews.
Limited chance, you can do it also anywhere. It's sometimes when you look at this video, you think like, oh, you are using very sophisticated techniques. No, that's not right. That's not right. You can just build your own electromagnets, okay, and we can help you with that, okay? Then you need a microscope, which everybody has, right? You have microscopes here, right? Then putting this electromagnetic system using some software, well, you need collaboration. You need engineers in your group. Not because you are, let's say, interested in biomedical applications, it means that you work with engineers. We engineers, we work with also people with medical background, microbiologists, because we don't know how to culture this cell. We don't know, right? So you have to work in a group.
Okay. How can I guarantee that it will not be attacked by the immune system? How can I guarantee that these microrobots will not be attacked by the immune system?
Well, I think you will have to help us with this. We are not thinking about these problems now. We have enough problems to think about.
Yes,
well, but it's a very legitimate question, a very legitimate concern. Right? But all these microbes might be attacked, right?
You said that we sometimes use bacteria.
Yes. It's you're right. Hold on. It's been proven that magnetic bacteria can live in blood for 48 hours. Magnetic bacteria, they can live inside our blood for 48 hours into the eye. So the question now is, during these 48 hours, would the swarm of magnetic active bacteria localize the drugs within the vicinity of some cells? You understand? But of course, this is a lot of concerns, and in this research, a lot of challenges to be overcome. Yes.
First of all, I'd like to thank you for this simple way of getting the other information. It's a vast field. Doctor, I have many questions. So the first one is about getting the basis of bacteria. Okay. What is the type of bacteria we use? Is it pathogens or have no pathogens? Okay. The other one, it is linked to this question. Okay. This question that say we use E. coli, and you see that. Okay. E. coli, as we all know, that bacteria that changes size, normal size, it becomes pathogens. Okay. Like many types, if it changes this or its condition, its normal condition, it becomes pathogens. Many of them. Okay. How can we deal with something like this?
So I want to make one thing clear. Back in 1970, there was this professor in Harvard, Professor Russell. He made a very nice lecture about microorganisms. He showed that, I will answer your question, but I will get around it, okay? So I'll get back to you in a bit.
Okay.
He showed that he had like a wonderful audience then he asks something. If I were to scale 2,000 times smaller, what would happen? If I were to scale my size down 2,000 times smaller, what would happen? The answer is I won't be able to move. Then, how about microorganisms? Do they have legs and arms and feet? They don't have. They have different propulsion mechanisms, right? They have different morphology. So the answer is, if we scale your size down, you won't be able to swim, right? If we got a fish that's that big, and we scaled its size down, and its reciprocal motion will not allow it to move. Because in that scale, there's no inertia. These micro robots or these bacteria or sperm, they don't know anything about inertia. They don't know that they have weight. They can speed up or slow down in no time, and that's excellent. Now, I return back to your question. We benefit from bacteria, from sperm, by just taking their designs. I'm trying to fabricate a micromotor. How am I going to fabricate a micromotor? With the current technology we have, with the current technology in the Silicon Valleys in California, in let's say clean rooms that we have even in Egypt, you cannot fabricate a small propeller. You cannot fabricate a small motor. And if you fabricate a small motor, how would you provide energy in that scale? You understand? So nature have provided solutions for us. Nature have provided excellent solutions. And the smallest motors have been provided centuries ago. And you can see them in the E. coli, in the bacteria that you have. So what we do is, we don't interfere with let's say, with anything biological, with the bacteria or the E. coli. We just check how they swim, and we try to mimic this way. Because we cannot scale down the robots that we have now.
Okay, thank you. The other one. What is the magnetic field? What are the characteristics of the magnetic field? Okay, characteristics of the magnetic field.
Well, for magnetic fields, but this question will raise another problem. It's like, what are the magnetic fields we are using? There's one problem with magnetic fields. Magnetic fields, they don't propagate much, right? Then you say, okay, if I want to build magnets around the human body, would I be able to control the motion of a bacteria? The answer is no. But let me explain this. If you have a magnet, and we watch this movie X-Men, and the whole magnet is nice, but you don't care about physics, right? I cannot apply, if I have a small magnet, the projection distance of the magnetic field is that much, let's say, okay? The projection distance of the gradient is even less. And to provide magnetic force, you will have to provide magnetic field gradient that's very small amount, very small distance. Let me tell you something. You know this bacteria that I showed you? In order to stop its motion, you need magnetic field provided by a modern MRI. It's a tiny thing, but you cannot stop its motion. That's why it moves towards the reference, but doesn't stop. You understand? Because its dipole moment is very, very, very small. So when you multiply this almost zero by the maximum gradient you can provide using a modern MRI, you get a zero force. So the propulsive force of the plasma is higher than the magnetic force that you can use to solve the bacteria. So characteristics, you have to design a magnetic system that can provide both magnetic fields and magnetic field gradients. But don't work hard on controlling the system with gradients, because it's like a dead end. It's like the projection distance is very small and it will not allow you to control microbes inside the human body.
Okay. The last question. Sorry for this. Okay.
Take it easy.
How to avoid the bad effect of hydrogen peroxide inside the body? Or we use some things that inject oxygen inside what we need.
Yes, my good friend. You won't be able. Don't use the robot that injects oxygen in your body. Don't use it. Don't use this particular robot in biomedical application. Don't. Just use other robots. And you can use a robot with well, what we do is put some chemicals that